In this video, we will explore some features, common uses, and operation of a dynamic mechanical analyzer, also known as a DMA. A DMA is an instrument that can apply forces to a small sample and measure the resulting displacements. These forces can be applied dynamically, for example with an amplitude following a sine wave pattern at different frequencies. DMAs also feature an environmental chamber to control the temperature of the sample and ambient humidity. DMAs have multiple uses in materials characterization. A common use is determining the glass transition temperature, or TG, of polymers. This can be done by observing the elastic properties of a sample while increasing its temperature. The TG of a polymer is useful for evaluating its suitability for service in different environments depending on the desired properties of the polymer. It is common to study the effects of different processing parameters on the TG of the final material. Moisture content, recycled material content, processing temperature, and degree of cure for thermosetting polymers are some examples of material characteristics that can have an effect on the TG of the final material. In some applications, it may be desirable to optimize material processing parameters to produce a material with a high TG. A DMA can be used to characterize the properties of viscoelastic materials like plastics and rubbers over a range of temperatures. This can be useful data for component design with viscoelastic materials that are subject to stress and high or low temperatures. Creep and stress relaxation are two characteristics that DMAs can be especially useful to study. A DMA can also be used to measure the elastic properties of a thermosetting polymer while it is curing. The results can be used to design manufacturing processes involving resins and adhesives. In addition to these common uses, there are other more niche applications of a DMA. Whenever elastic properties at different temperatures or humidities are required, a DMA may be of use. A DMA uses various electromechanical components to apply loads and record displacements. They are optimized to produce precise measurements at relatively small forces and displacements compared to other materials testing equipment, sometimes working on the scale of less than a newton of force. A linear motor is typically used to apply forces to the sample. A linear motor is similar to a regular motor in that it uses precise electrical currents to produce forces, but it produces linear translations instead of rotation. In conjunction with the linear motor, the position of the force applicator is measured precisely by a method that is typically proprietary to manufacturers. To hold the sample and apply loads, a fixturing system is needed. There are a variety of sample fixtures available, some examples being 3-point bend, dual cantilever, tension, and compressive fixtures. These are typically made of steel or stainless steel for high stiffness and temperature stability. An environmental chamber can be used to control the temperature of the sample. Electric heating elements and fast-flowing air are used to heat up the sample with quick response and minimal thermal gradients. The sample can also be cooled in the same fashion using an external air cooling device or a liquid nitrogen supply. The relative humidity can also be controlled inside the chamber. Systems are also available that can submerge the sample in a liquid while it is being tested. We will now use the DMA to determine the TG of an epoxy prepreg carbon fiber composite sample. This value is sometimes available on the material datasheet specified as the DMA TG, but can be affected by many factors present in the storage and processing of the material. To determine the TG, we will record some material properties as we increase the temperature of the sample. The material properties we will record are the storage modulus, loss modulus, and the tan delta, also known as the loss tangent. These properties relate to the energy that is stored and the energy that is dissipated when a material is deformed. These values can be determined by applying a sinusoidal force to a sample and recording the displacements. Viscoelastic materials will have a phase shift in between their forces and displacements. The loss tangent is calculated based on the number of degrees the two curves are out of phase by and can be used to calculate the two moduli. The storage modulus is a function of the overall forces and displacements and energy that is stored in the material. The loss modulus has a similar definition but relates to energy that is dissipated. If a material is an elastic solid, all of the energy expended deforming it is returned when it springs back. An elastic solid will have displacements that follow the applied forces and will resultingly have a high storage modulus and low loss modulus. If a material is a viscous fluid, all of the energy expended deforming it is dissipated in the material. A viscous fluid will have displacements out of phase with the applied forces and will have a small storage modulus and large loss modulus. Viscoelastic materials will be somewhere in between these two scenarios. Many polymers and polymer composites are viscoelastic. We can use a DMA to record these three properties versus sample temperature. As we approach the TG, the stowage modulus will begin to drop. The intersection of two lines drawn tangent to the stowage modulus plotted on a logarithmic scale marks one definition of the TG. The loss modulus will begin to rise and then typically drops. The peak value can also be used to describe the TG. The loss tangent will peak somewhere around this temperature as well, and this third event is also commonly used to describe the TG. After performing our DMA run, we will obtain these values which can be used to determine the TGs of our material. We will prepare our small samples according to ASTM D7028.
We will produce a laminate measuring 60 mm by 12 mm by 2 mm thick with the fibers oriented along the length of the sample.
We will use a diamond saw to precisely cut the sample to the required size without damaging it. We will then measure the dimensions and the mass of the sample with precision measurement tools and record the values. We will install the selected fixture into the DMA. For our fibre-reinforced thermoset samples, we will use the 3-point bend fixture, which lends itself well to stiff samples. We will place the sample in the DMA and align it. We will now program the test. We will apply an oscillating force of 10 newtons at a frequency of 1 Hz. We will ramp the temperature at 5 degrees C per minute, starting at room temperature and ending at 230 degrees Celsius. The datasheet for this material lists a TG of 180 degrees Celsius, and it is recommended by ASTM to surpass the TG by at least 50 C. It is common to start at lower than room temperature so that more complete material data is produced. ASTM also recommends choosing an upper temperature limit that does not degrade the material. Measurements taken after the sample has degraded will not help us determine the TG and can potentially soil the DMA. The degradation temperature of a material can be determined with a thermogravimetric analyzer, or a TGA. A TGA will measure the mass of a small sample while its temperature is increased. As the material starts to degrade at high temperatures, it will typically begin to lose mass. Solid molecules react with ambient gases, each other, and themselves to produce smaller gas molecules. The results of this test can be used to determine a temperature for the upper limit of a DMA run. We will now conduct the DMA test. We can see that as the temperature increases, the stowage modulus begins to drop. We can also observe the loss tangent and loss modulus peaking and dropping as expected. The data from this test is available to download at the link below. The TG can be determined using the methods described previously. In addition to determining the TG of polymers, DMAs can also be used to obtain other information as well. The stiffness of polymers versus temperature can be used to design manufacturing processes like thermoforming. The elastic properties of thermosetting resins as a function of degree of cure can be used to simulate and manage the effects of shrinkage and thermal expansion during composite part manufacturing, leading to tighter tolerance parts. DMA data is not just useful for manufacturing, however, and can be used to engineer components containing materials like rubber and plastics that are exposed to a range of temperatures while also subject to mechanical property requirements.
Thanks for watching. To see more virtual labs and learn more about composite materials, make sure to subscribe to the CKN YouTube channel.